Hello again, welcome back to the third part of superposition. Today we are going to do Rayleigh criterion. Now the Rayleigh criterion talks about the diffraction of images when they are seen inside a camera or other optical device. Now what happens inside the camera is that point-like objects, let's say this image is a single dot, when it passes through the camera due to diffraction, the image is going to form a large dot with a maxima in the middle and other rings around the sides. Now this is a diffraction pattern and it means that the next object cannot be too close, otherwise the images of the two objects will overlap and then you will not be able to tell them apart. So let's take a look over here. We have got a first image which is a round circular image of a small object, and due to diffraction you can see the single slit diffraction envelope is right there, okay, below the image. Now two images are just resolved if the central maximum of one image coincides with the first maximum of the other. Now, so how close can we put the images together? Rayleigh criterion says that we can put them this close. Now this close because the central maximum of one image will coincide with the first minimum of the other, meaning that the central maximum of the second image is over here. As you can see, the maximum of the image coincides with the minimum of the other image. This is the Rayleigh criterion. The same over here, the maximum of the first image coincides with the minimum of the second image. Now, in order to do Rayleigh criterion, there are two formulas you need to know. First of all is the minimum angular resolution of the camera. Now, when the image goes into the camera, it spreads out, and they are going to have a minimum angular spreading due to the camera. Now, the theta minimum is given by the formula B theta minimum is approximately equals to 1.22 lambda, and that is given because the circular aperture. Alright, so the formula is slightly different from single slit diffraction. So this is formula number 1. Now, what about formula number 2? Formula number 2 relates to how far apart the two objects can be if they are to be resolved. Now, how far apart two objects can be given the angular separation of the two objects is given by this formula. Alright, that the angular separation of the two objects will be given by theta r. This is the angular separation of the two objects outside the camera. So this is the inside the camera formula, and this is the outside the camera formula. Now, in order for the object to be resolved, it all depends on whether or not the theta of the target is bigger or smaller. Now, if theta of the target is larger than the minimum angular resolution of the camera, all right, then we will say that the images are resolved. Now, once again, if the theta of the target is equal to the minimum angular resolution inside the camera, we'll say that images are just resolved. And then finally, no prizes for guessing what's the last one. Okay, if the angular size of the target, theta target, is less than the minimum size that can be resolved in the camera, then the images are not resolved. Okay, so let's take a look at the Rayleigh criterion. Now, the largest aperture of the largest telescope in the world is approximately 5 meters, so this is B equals to 5. Now, can I just specify that this is the largest optical telescope in the world, because there are much larger telescopes in the world which are radio telescopes. If the separation between the moon and Earth is approximately 4 times 10 to the power 8, this is R, and the wavelength of visible light is 500 nanometers, this is lambda, and the minimum separation of the moon that can be resolved, which is S, equals to question mark. So our first task is to find theta minimum inside the camera. So theta minimum will be 1 times 10 to the power of -7 radians. That's a very, very small feature that can be observed. Now, using the outline formula to approximate separation between objects, S equals to R theta, we take this value of theta and we put it inside here so that it is just resolved then we get 40 meters. So a 5-meter telescope on the Earth cannot distinguish any object that is smaller than 40 meters on the moon. That means to say anything that's smaller than a building, a large building, can't be seen. That's why we can't use optical telescopes to look at all the landers and equipment that people have left on the moon. Now the resolution limit of the eye is 3 times 10 to the power of -4 radian. So this one will be theta min. At a distance of d from the eye, 2 persons stand with a lateral separation of 3 meters, that's s. Okay, the 2 persons to be just resolved by the eye, resolved by the eye, that means this is theta target is equals to theta min. D should be, okay, so this is the 2 people standing separated from each other. Right, this is a distance d, and they want to know that, this is a distance s. S is 3 meters, and then we have theta target equals to a certain value, theta min. All right, so that's a straightforward application of s equals to r theta, and then r will be 10 kilometers. That means to say if 2 people are standing 3 meters apart, you can tell that there are 2 people even if they are standing at 10 kilometers. I think this is a bit far-fetched. And most of all, Singaporeans have terrible eyesight. So I think that maybe it under ideal conditions, because to be honest, Singapore's air is so polluted that you can't even see more than 6 kilometers away. Next, we're going to have multiple slit diffraction. Multiple slit diffraction consists of 2 kinds, which is slits with 6, 7, 8 slits, or slits with thousands of slits, such as the diffraction grating. Now, what is a diffraction grating? A diffraction grating is a grating made of molecular-sized slits, all right? There can be up to 600 or even 1,000 slits per millimeter. So, the formula for this diffraction grating is the same as every other diffraction formula for 2 or more slits, which is d sine theta n equals to n lambda. Now, how do I find d though? Well, in this case, d will be 1 over n, where n is the number of slits per meter. So I'll just put this capital N, although it's not supposed to be capital N. So n is the number of slits per meter. Now, so let's say there's 600 slits, okay? So then, therefore, d in this case will be 1 mm, 1 times 10 to the -3, divided by 600. In this case, if there are 600 slits per mm. Obviously, the number will be different for every question. Okay, so narrow beam of chromatic light falls at normal incidence on a diffraction grating. Third order diffracted beams are formed at angles of 45 degrees to the original direction. So over here, this is 45 degrees, which is the third order diffracted beam, theta 3. So over here, n equals to 0, down here, n equals to 3. Determine the highest order of diffracted beam produced by this grating. The highest order diffracted beam will be the n where theta is equals to 90 degrees. So let's write down d sine theta 3 equals to 3 lambda. Then d sine theta n equals to n lambda. Solve for n. Alright, so basically what we're going to do is that we are going to fill in the values over it. Okay, so therefore, okay, we put d sine 45 is equals to 3 lambda. D sine 90 is equals to, solve for n where theta equals to 90 degrees. So it's n lambda. Okay, so we can use a calculator to find that n is equals to 4.24. Therefore, the largest value of n is 4. Since we cannot see the 0.24 of diffraction order, right? So that means that n equals to 4 will be over here. Then over here will be n equals to 4.24, which is not seen. All right, so the highest order is 4. Now, how many dots actually are visible? Okay, so this is n equals to 1, n equals to 2, n equals to 3, n equals to 4. Then on the other side, n equals to 1, n equals to 2, n equals to 3, and n equals to 4. So the total number of the maxima that is seen will be equals to 4 times 2 plus 1, which is 9 maximas in total. Okay, so there'll be 9 dots on the screen. Okay, let's move on to question 14. A diffraction grating with 250 lines per mm is placed in front of a monochromatic source of red light. So 250 lines per mm, so the D is equals to 1 times 10 to the power of minus 3 divided by 250. Now red light, we know that the wavelength is more or less equals to 650 nanometers. So later we can check this number. A screen placed 200 centimeters beyond the grating has red light at certain positions on the screen as shown below. Now notice that the they don't actually give you this you know, what is the correct position. So what we can do is that we can use this to give us the value of theta 2 over here. Okay, so let's do a trigonometry. This is theta 2 and this is 2 meters. And then this is 145.6 minus 72.7. So this over here will be 145.6 minus 72.7 cm. Alright, so later on we have to convert it into meters. Okay, so let's use theta 2. Theta 2 is equals to, using a calculator and a little bit of trigonometry, we can find that theta 2 equals to 20.03 degrees. Okay, so now we can find a value for the wavelength of red light using theta 2. Using n equals to 2, we can get d, which is d sine theta 2 is equals to 2 lambda. So 1 times 10 to the minus 3 divided by 250 sine of 20.03 is equals to 2 lambda, giving us 6.85 times 10 to the power of minus 7 meters, which is 685 nanometers. Okay, that's reasonably close, okay, to our initial guesstimate of 650 nanometers. Okay, so that is how you'll do it. Now, state one advantage and one disadvantage of determining the wavelengths by observing the second order instead of the first order. The advantage is that the higher order diffracted beam will be bent through a larger angle, so it reduces the percentage error in the measurement, and it's easier to measure the angle and distance as they are larger. Now, what's the disadvantage is that there are dimmer images. Okay, so position of fringe is more difficult to determine. Another one that they didn't mention is that the fringes are actually blurred or larger, so the uncertainty of the position is increased. All right, so the fringes, as they go out, right, the size of the fringe actually kind of spreads out, so that makes it a little bit more difficult to measure. Now discuss how the pattern obtained would be different if blue light were used in place of red light. So remember that blue light is kind of like around 450 nanometers as compared to the red light, which is around 685 nanometers that is found in part A. So what happens is that in the equation d sine theta n equals to n lambda, if the lambda decreases, then theta n also falls. Right, so what happens is that the angle of the diffracted beam mixed with the normal diffraction grating would be smaller for the blue light. Okay. The number of order of spectrums will also increase. That means to say, previously we could see only 1, 2, 3, 4, 1, 2, 3, 4. We could only see up to n equals to 4, but with the blue light, you might be able to see up to n equals to 6 or something like that. All right, so that will be the maximum order that's observed will also be increased. So probably it wouldn't say the maximum number of order of spectrums, but rather the maximum order of maxima would be increased. We didn't use a spectrum here because we only use a single color light. Spectrum refers to a rainbow. Okay, so we did not use multicolored light, we only use a monochromatic light source. So that's the end of question 14. I'll teach you guys stationary waves next week.